Hello, everyone. It's Sandra here, and welcome to the second episode of Worm Science. In these videos, what I'm doing is I'm taking published research and I'm breaking it down not only as a person with expertise in research methodology, but as a personal worm farmer who raises worms for my own recycling and composting purposes. So I hope I'll be able to give you how to read this research with a critical eye. And at the end of the research discussion, I'm going to give you my takeaways on what we can do as worm farmers to maybe learn from this bit of published research. So I know research, and that's what I hope to be able to bring to this discussion is my knowledge in research to help you better understand your worms. All right, so let's get into it. The study we have today is an interesting one. So here's the title page of this research paper, and you can see right away, I hope, that it's not a typical publication. It's got a number 17 at the front of it. That actually is chapter 17. This is a chapter in a book on worms and soil science. So right away, you can tell that it's not just a single study studying one factor. We're looking at growth and reproduction of worms today, but we're not going to just look at a single study. And the researchers themselves give a hint on what they're doing right in the title. After the colon there, they call it a review. And the word review has a very defined meaning in the world of research, and that's a review of what we call the literature. It's not Shakespeare. The literature means looking at published research and pulling from it tidbits from here and there and putting it together in a more coherent fashion. Reviews are extremely valuable for people who want to sort of cast a broad net to get information from a variety of sources rather than just this research pair. So in that way, it's a good thing. They're casting a broad net and they're bringing in the best of the best from wherever they may find it. I'm going to get into the limitations at the end of this presentation on why this may be a bit of a downside as well. But for the moment, let's just say that this review is something that we can look forward to bringing in a lot of information. And there certainly is a jam-packed information in this Worm Science episode 2. The other things that we can learn from this title shot of the paper is that we see a familiar name on it. Dr. Dominguez was in our first episode 1. So if you look down at the bottom of the page, you can see the title of the book where this was published, Soil Zoology for Sustainable Development in the 21st Century. The book itself was published in 2004, meaning that this chapter was probably written a year or two before that. So it predates the episode 1 science done by Dr. Dominguez, probably by at least 20 years. And as I said in the first episode, the date of publication of research is one of the factors that we look at when we decide how credible the research is. Is there more science that's gone on in more recent years that could better illustrate the topics under study? I think these researchers have done a pretty good job with jam-packing this chapter with really tasty tidbits on worm science, and I hope you'll agree with me by the end of this presentation. So I wouldn't discount the information they're presenting just yet, just because it's over 20 years old. All right, let's get into it. I always like to give you the full citation of the research so that you may look this up. The full text of this research is available online, and I'll also give you credit for the pictures that I'm using in this presentation today. Some of them were on Dr. Dominguez's website, as well as some in the common domain. So the topic that we're looking at today is the growth and reproduction of composting worms. Now, you know that cocoon production and how quickly and how much worms grow is critically affected by the conditions that we put these worms in. There's factors like moisture and temperature and pH, as well as the bedding itself that we choose for these worms. Research has shown that there's a relatively narrow range in which these worms will optimally operate. And I'll be getting into some of those numbers and the different parameters in this presentation. And if you exceed those ranges, you know, worms have sometimes a very dramatic response. They can cease reproducing. They may leave the area. So they may vacate. They may cease development and growth. And in worst case scenarios, they may die. So these parameters that we'll be discussing today, outside of the ranges which we may inadvertently introduce into our worm bins, can have some very dire consequences for our worms. So I think it's a topic that each of us who raises worms is really going to take away something from this presentation, I hope, that will help us keep our worms safe and healthy going forward. So an outline of my presentation today, I'm going to be giving you some quick fire facts from Dr. Dominguez and Dr. Edwards. They give just bang, 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 bang on the two Icenia andri and the Icenia fetida, the two collectively known as red wigglers. They just give us a whole rapid fire facts that they've derived from their review of previous research, the review of the literature. So I'll be going through those facts with you. I think they're fascinating. And then they get into the conditions in which worms are raised. And I'll be outlining the temperature, the moisture, and the pH conditions that are optimal for worms to be raised in. And finally, I'll conclude by looking at some bedding sources and the different growth and reproduction rates in different types of bedding. And this also, I hope, will help inform you as a worm farmer. So first, let's get into those quick fire facts. So as I said, the researchers covered prior research on these facts for both Icenia fetida and Icenia andri. And these are the facts that they put forward in their review. The life cycle from cocoon to an adult worm, sexually mature adult worm depositing the first cocoon, takes between 45 and 51 days in optimum conditions. The time for any hatchlings to get to maturity, sexual maturity, takes 21 to 30 days. Again, optimal conditions. The time for cocoons to be laid after mating is 48 hours. Sometimes you'll see that swollen clitellum on an earthworm, and that's when the cocoon is being formed. So cocoon production. On average, these worms produce an average of 0.35 to 1.3 cocoons per day in optimum conditions. Amazing. All right, hatchling viability. How many of them are born alive? That is 72 to 82% in optimum conditions. Reasons that hatchlings may not be viable could just be a developmental anomaly that happens in the cocoon. It could be that the resources of the cocoon were not evenly shared among the hatchlings. It could be that some hatchlings or a single hatchling emerges early, and the others are subject to exterior conditions, whether it be a drying of the interior of the cocoon or an invasion of the cocoon by a parasite, or perhaps by bacteria. So there's a variety of reasons why subsequent hatchlings may not survive, or perhaps the first hatchling to emerge was not fully mature when it did so, and it did not survive. All right, the incubation period, 18 to 26 days. Now, when cocoons take longer than that, and they can certainly go into stasis for extended periods, those are in those extreme conditions that we've all experienced in our bin, where we go, why aren't the cocoons, if you have a cocoon nursery, why aren't the cocoons hatching? And that's perhaps not suboptimum conditions. Maybe the bedding isn't well inoculated. Maybe the temperature and moisture aren't optimum. So those of you who incubate cocoons I would be really interested in hearing your experiences on how long your cocoons take to hatch. All right, how many hatchlings do you get per cocoon with these two Icenia species? Well, you get between 2.5 and 3.8 on average. So I know people have told me that they've seen more than that, but I've also seen cocoons where only one comes out, and you go, where are the rest? All that effort and only one worm emerges. All right, and so for these Icenia species, the maximum life expectancy, 4.5 to 5 years. In natural conditions in the wild, it's going to be considerably less, probably 40% of that. I would say the researchers mentioned 594 days in one of their pieces of research that they were talking about. So if the worms are in the wild, they will live less long. And also it's difficult for us to maintain optimum conditions throughout their life expectancy. So we may, as home worm raisers, we may also get less than 5 years total out of our Icenia worms. All right, let's get into the conditions that these worms do best in. And the first condition we're going to look at is temperature. Now, here are some facts that the researchers gave us from the literature on raising Icenia worms. In terms of temperature, at 10 degrees, your worms are going to slow down feeding and reproducing. So 10 degrees Celsius is 50 degrees Fahrenheit. And so don't expect your worms to move very quickly, eat very quickly, or reproduce very quickly. They're going to be more like turtles. At 4 degrees Celsius, which is 39.2 degrees Fahrenheit, both reproduction and growth stops. The worms don't die, but they stop reproducing and they stop growing, which also means they're going to stop eating. Now, they are going to survive. In fact, Icenia worms can even withstand short duration at freezing temperatures. However, absolutely, if you have outdoor worm bins that go down to those temperatures, you will definitely need to temper your expectations and stop feeding those worms. Okay, let's look at the upper range of temperatures. The researchers reported that at 30 degrees Celsius, which is 86 degrees Fahrenheit, the worms actually suffer. They will perhaps vacate the area if they can. They will certainly not be actively reproducing and growing over 30 degrees Celsius. And it's an interesting reason. It's actually oxygen starvation. And you might think, well, why would my bin be starved of oxygen at higher temperatures? What is it about higher temperatures that deprives the worms of oxygen? Well, it's actually the microbes. The reason that worm bins are so incredible is they're full of microbes. And so those microbes actually get very active at higher temperatures, over 30 degrees, over 86 degrees Fahrenheit. the microbes pick up their speed, and the microbes consume all the oxygen, depriving the worms of oxygen such that the worms go into survival mode, and or like I said, they will vacate, and in worst case scenario, they will die. The researchers gave us this chart, and my apologies for not being able to reproduce this chart. This is a screen grab from this 20-plus-year-old study. And so the printing is a little bit fuzzy. However, I'll walk you through it. There's a lot going on here. This figure is titled The Growth of Icenia fetida at Different Temperatures. And you'll see that they outline 4 different temperatures, starting at 10 degrees Celsius or 50 degrees Fahrenheit, and going up in 5 degrees Celsius increments to 25 degrees Celsius or 77 degrees Fahrenheit. And they have along the left-hand axis of this graph, they have the mean earthworm weight. So that's the average weight of the worms. So we're looking at growth of the worms here. And along the bottom axis, we're looking at time in days. Now note the chart only goes to 70 days. The worms, if you remember, were mature in the 45 to 50 odd day range. So these are sexually mature worms by 70 days old, but they're still young worms. They're not juveniles, they're adults, but they're still fairly young. And so this chart does not cover the entire lifespan of the worm. It just covers the first 70 days. Now you'll notice 4 lines on the chart, and I've tried to put little blobs of color on those 4 lines so that they correspond to the different temperatures, hopefully to make it a bit easier for you. The very lowest line on the chart, the one that's dabbed with the pale blue, is for the 10 degrees Celsius or the 50 degrees Fahrenheit. So no surprise there that the earthworms are going to grow slowly at 10 degrees. Remember, I said that growth slows right down. Well, yep, there it is in a chart. The growth is very slow over 70 days. It's slow and steady. The worms are alive, but they're not growing very quickly. In the other 3 temperatures, the 15, the 20, and the 25 degrees Celsius, that range goes from 59 degrees Fahrenheit to 77 degrees Fahrenheit. The worms grow very quickly, and then they peak out, and they actually start decreasing in size. If you notice, each of the arcs of those lines reaches a peak at about sexual maturity, about 45 to 50-ish days old, and then it starts to decrease. And they start to come together. The 3 lines start to come together. So by 70 days, there really isn't much difference between the 15 degrees Celsius and the 25 degrees Celsius in terms of the growth of the Icenia fetida. Now, this chart only goes to 70 days. We don't know where the lines go beyond this. So speculating is going to be impossible. We don't know whether those 3 upper temperatures drop any further in terms of the average weight of the worms, or they flatten out, or they start like a roller coaster and start going up again. We don't know that. All this research shows is what it shows. And I said that in the first episode. We always want more from research, but it only can tell us what it can tell us. To speculate beyond that would be irresponsible on the part of the researcher. So what we can learn from this then is 10 degrees Celsius, slow growth. The other, anything greater than 10 degrees, rapid growth, that at the minimum is going to flatten out and come together. So not make a big difference between the 3 temperatures depicted here. So now let's take a look at moisture and its effects on the growth of Icenia andri. Again, one of the worms collectively known as red wigglers. Okay, so again, my apologies for this chart. This is the best I could do as a screen grab from an old copy of the journal article. So what we're looking at on the left-hand axis is the average biomass, basically weight of the individual worms. And along the bottom again is how many days. And this graph chart takes us up to 44 days. So that is just before sexual maturity. So we're looking now at growth prior to the point that these worms become sexually active. Now, the different colors that I've dabbed on there correspond to different moisture levels. The chart begins at 65% moisture and ends at 90% moisture. And you'll notice that there are basically two clusters of lines. On the bottommost growth, or the slowest growth of worms, is in the 65, 70, and 75% moisture levels. And the highest growth rates are found in the 80, the 85, and the 90% moisture. Now, these are in pre-adult worms, pre-sexually active worms. And also notice the trend lines on this chart. The lines are not linear. They're not just steady up. There's some curvature happening to these lines. Again, we can't speculate whether the curvature is going to continue in that direction or it will loop around and reverse on itself. We don't know, but it's interesting to note that the growth is not linear. So, you know, more moisture seems to be better, but then those lines, at least a couple of them, seem to be trending down. And so, you know, do all the lines eventually meet up at some point in the future lifespan of the worm? That would be interesting. And for those of you who have moisture meters that you can actually measure the moisture content of your worm bins, please put in the comments what moisture levels you use for your worms and your results going forward beyond the point that the worms produce cocoons, because I think others would be greatly interested in learning from your experience. These researchers also noted that 50% moisture was the minimum to raise worms, you know, for a prolonged period of time. Most of us who raise worms will tell you that we've had shorter time periods where worms have been exposed to less than 50% moisture. You know, they've dropped on the floor or on a dry piece of cardstock or something, and you find them and they're still alive. Usually that's a very short duration, but the research shows that 50% is the minimum level needed by the Eisenia fetida worms. This next condition surprised me, and that's the pH preferences of Eisenia fetida. So you'll notice on the left axis, the researchers called this earthworm abundance. So they looked at whether the worms moved towards or away from these varying conditions. And it's a slam dunk. The preferred pH is 5.0, very acidic in terms of what I was expecting. I was expecting that the worms would prefer something more neutral or even more basic, but nope, they prefer acidic conditions. Not, you know, it's slightly acidic, but it's definitely on the acidic side. Now, having said that, the researchers caution that at 4.5 pH, so just half a pH lower, the worms will start actively moving away, and that any further drop in pH could be lethal to worms. So it's so interesting that the worms are drawn to a pH that is so close to an end of a range for them. They've got all those upper levels, the neutral pH and the slightly basic or alkaline pHs, and they really don't seem to prefer those at all. Very interesting to me. Now, where are you going to find acidic pH conditions? Well, you're going to find it in a microbially active zone, a bacterial active zone is where you're going to find those acidic conditions. So in terms of bedding, well, the growth and reproduction of worms, it depends on the quality of what we give them for their homes to live in and to consume. And this will ideally, ultimately increase the microbial activity. And it's that quality that the worms look to invest energy in either reproducing or growing larger. Now, Dominguez and Edwards present something that they call a case study. And from what I can gather, this is basically out of their own lab, the lab results that they've been collecting on looking at different bedding sources for Yersinia andri. So this isn't published research. This is just observations and measurements that they're making in their lab, raising worms in different conditions and seeing which bedding sources allows worms to reproduce more quickly and which ones allow the worms to grow more quickly. Okay, so let's take a look at this chart. There's a lot going on here. So let me explain what we're seeing. There's two intersecting lines, and they represent either growth that goes from left to right, or reproduction, which goes from top to the bottom. Now, the bedding materials were dried out and they were mixed 1-to-1 based on their dry weight with something we've heard of before with that sewage sludge. Again, the sewage sludge was dry, the bedding materials were dry, then they would be moistened and the worms would be added. The black squares on this chart, they represent the data point for each of the materials tested. Notice there's no numbers on the plot. It's a visual comparison to show the relative rates of growth and reproduction of these materials rather than giving you a numeric comparison at this point, although I'm going to be getting into some numbers in a few minutes. The sewage sludge, you see that in the upper left quadrant. It's shown here and it acts as a control. The sewage sludge was in every test. Remember, it's a 1-to-1 ratio based on dry weight. So sewage sludge, they tested it all by itself to sort of say, well, what growth and reproduction can be accounted for by the sewage sludge alone that's present in these materials. So in that sense, it acts as a control, even though this is not an experimental design, there's nevertheless a bit of a control there with that upper left point next to the sewage sludge. And then how we read the chart, let's take a look at grass clippings, which is right next to the sewage sludge. The sewage sludge and grass clippings mixture, which is marked by just the word grass clippings, notice it had slightly increased reproduction because it goes a little bit further along the arrow that goes top to bottom, but decreased growth. That's the line that goes left to right. So it's a little bit further left of sewage sludge, which means it has less growth compared to sewage sludge alone, but slightly more cocoon reproduction, because it is a little bit further down the line that goes top to bottom. And that's how we're going to read all of these data points. So let's take a look at growth. And if you look at that data point, you slide your eyes over to the right and you see the data point next to the words food waste, you'll see that that point is the furthest along that line that goes left to right. That's the line that represents growth. And so the maximum growth, the maximum weights were found when sewage sludge was mixed 50-50 with food waste. That outperformed any other thing mixed with the sewage sludge in terms of growing the worms, making them grow nice and big. So the researchers do give some numbers for this growth. They said the average weight of the worms, given the food waste and sewage sludge mixture, was 0.76 grams. So now let's go to the other end of the scale and look at the smallest worms, the ones that grew the least and had the lowest growth rate. That was the mixture of sewage sludge and sawdust. These worms only average 0.58 grams, and that is 72% slower growth than the worms fed food waste. So you can just imagine the microbial differences between a bedding mixture that has sawdust mixed with sewage sludge and a bedding mixture that has food waste mixed with sewage sludge. And these researchers found that growth rates reflected that change in microbial richness.
In terms of reproduction, cardboard, then sawdust, then paper, then pine needles did the best, and the researchers give us a couple numbers in this group for comparison.
So let's take a look at the mixture that had paper and sewage sludge. In that, the researchers give us the number that the worms produced an average of 2.82 cocoons a week. And in the cardboard mixture, this increased to 3.19 cocoons per week. So compare this to the reproduction in sewage sludge alone, that was 0.05 cocoons a week. So this represents a 5 to 6-fold difference in the number of cocoons produced every week if you took sewage sludge alone versus sewage sludge mixed with either paper or cardboard. Okay, so let's get into my limitations on this book chapter. So it wasn't primary research. Primary research is where the researcher actually does the work. Secondary research is when they rely on the work of others. And they did a lot of that. All of those facts and things, figures I was reading out, these researchers went and they relied on the work of others to pull out those facts. And where they tried to do primary research when discussing the different bedding types and cocoon production and growth, they did not follow research protocols in reporting on their methodology, their own limitations, reporting of their results in a structured way. So it fell short methodologically. So again, I'm a little bit of a nitpicker. That's my job when it comes to research. So I'm always critical. All right. So the other thing is a bit of a selection bias. This is research done by somebody we've seen before. And in our first episode of Worm Science, and, you know, looking at the same person's research over and over to shape our own knowledge and maybe to inform our own worm farming practices, it could be a danger there. That person may be basing his research on a point of view that maybe goes against the field or goes against the other experts in his area. And we could be blindly following somebody who is only showing us what he wants us to see. He could, I'm not saying it's an agenda that would have some negative tone to it, but everybody has a bias. To say that you're without bias is wrong. Everyone has bias. So using the same researcher twice, that introduces a bias into our worm science discussion. And secondly, researchers tend to use their own they cite themselves when they're talking about their research. So you can see how it becomes a little incestuous almost, that they go, oh, well, in previous research, and then they cite themselves. I mean, he would have said Dominguez 1998. in the paper, and he's well published. So he cites his previous work, sometimes done with other team members, sometimes done alone. And that has the potential to build a house of cards where, maybe one of those earlier studies is a weak link, and then others keep citing it. So that weakness is perpetuated in each subsequent study. And eventually the research could collapse because of that weakness. And I'll for sure introduce different researchers going forward so that we don't perpetuate that potential house of cards. Now let's get into my takeaways as a worm farmer.
In terms of bedding, if your purpose is to build your herd, you want to get as many worms as possible, then the rock stars are the cardboard, the sawdust, the paper, and the pine needles. So choose your bedding according to whether you want reproduction, so anything below the line, or growth, anything to the right-hand side of the chart. These researchers caution that any bedding type is going to set back both the growth and reproduction of worms when the worms are first added to the bedding. This especially happens with the pine needles, but all bedding types will have a setback.
I wanted to talk to you about that in terms of what we do when we harvest. When you put worms into new bedding, they are going to drop weight. And I think a brand new worm farmer probably has noticed that. You put brand new worms into brand new bedding and you go, they're not eating. Well, if they're not eating, they're losing weight, right? And they go, the food's still there. It's been 2 weeks. And more experienced worm farmers always say, give it time, give it time, give it time. The worms will get into the food when they settle into their new environment. And they do. We've all noticed that transition. But my takeaway is those harvest methods that leave the familiar behind, whether it's the bigger chunks of material that don't go through a sifter or we hand pick out, or we do a migration like I tend to do, and I leave like 25% of the bin in there and I scoop out the 75. Or we have a continuous flow system that we never take the worms out of their familiar bedding. Or we have a wedge system that we never take the worms out of the familiar bedding. Each of those conditions where we leave some of the familiar enhances the worm's comfort, if you like, and feeding activity and growth and reproduction. They're going to like it more. They're not going to go into that temporary halt in feeding and growth and reproduction. And so therefore your worm bin remains thriving and active. Okay, and my third takeaway is to do with temperature. And so I mentioned when we went through those results that cold temperatures need us to moderate our expectations for worms, and we could get into an overfeeding situation quite quickly. Anything below 50 degrees Fahrenheit or 10 degrees Celsius, especially as we approach that 4 degrees Celsius cutoff, we're definitely going to find that the worms are simply not going to be able to eat that food, inviting other pests to move in or the food to start fermenting. Now, some compost heat might be desirable, but I think all of us can realize that we could get our worms into a real pickle if we overfed at colder temperatures and they were not able to get to that food. And at the other end of the temperature scale, we talked about at 30 degrees Celsius that the bedding temperatures would start going anaerobic just because of the microbial explosion of growth, and that 25 degrees Celsius was the best for growth of those worms. Now, it turns out that 25 degrees is also best for cocoon production. So that's a really warm temperature for me here on Vancouver Island. I'm not going to expend a heating mats or anything to warm my worm bins to 25 degrees. 25 degrees is warmer than room temperature for those of us that keep indoor worm bins. But if you are breeding worms professionally, you definitely might want to look at that. That 25 degrees seems to be the sweet spot for the Icenia fetida and Icenia andri for both growth and reproduction, but just keep it below that 30-degree threshold so you don't run into those problems. That's my second episode of Worm Science. I hope that you found some interesting tidbits to take away. Please discuss in the comments your experiences with growth and reproduction, various temperatures, various moisture. Do you measure your pH? And also, of course, your bedding types and how those have affected your growth and reproduction. And, don't worry about the research mentioning sewage sludge. Basically, it's a manure, it's humanure. So, I'm going to be discussing different types of manure in the future in one of these worm series. So, human manure is just another type of manure. So sewage sludge, just take that in stride. Us worm people, we can handle it. All right, please subscribe and click that notification, and please join me, will you, in the next one. Until then, bye for now.